on a problem that I had to solve about 4 years ago involving an electrical network. This is one of my favorite subjects. This is a field I'm very, very good in. I studied under one of the world's foremost experts in network theory, Dr. Aaron Budak, who is just an absolute genius when it comes to dealing with networks and network synthesis. And I'm going to describe the problem here and then let you take a chance to try to solve it on your own. I'd recommend you try to solve it first on your own before you see my solution. This network is very unassuming. You have to be very careful. It looks extremely simple, but it's if you don't approach it right, it's really a bear to solve. So what I have are three resistors, or three circuit elements, passive circuit elements. They could be resistors, capacitors, inductors, or combinations. And they're connected in a loop in this fashion. There's three elements. And we have access to three nodes between the circuit elements. So I'm going to solve this circuit in general using generalized impedances. The Z's could represent resistor values, but this is just very general. These generalized impedances, which in AC circuit analysis would be complex numbers of magnitude and a phase angle, but in a resistor network these would all just be scalars. So what we have are three nodes, node A, B, and C. Node B is between element ZA and ZB. Node C is between ZB and ZC, and node A is between ZA and ZC. Now, keep in mind that what I had to do here is I had a network such as this embedded in a precision amplifier, and something wasn't quite right with the circuit, and I needed to determine whether or not the resistor values had shifted. But I couldn't extract the resistors out of the network. You'll be seeing in a little bit why that's the case, is I could not separate the resistors out to measure them individually to see if they had shifted. I only had access to the network between on these nodes. So rearranging the circuit is basically what I had access to is nodes A and B, and looking in to nodes A and B, measuring the impedance with nodes A and C open circuited. I could disconnect these three nodes, but I couldn't separate the resistors out. So we can measure the impedance or resistance between nodes A and B with A and C open circuited, and then I could measure the impedance looking into nodes B and C with this also open circuited, and then with these two open circuited can look in and measure the impedance looking in nodes A and C back into the network. So what we have in this condition is, note that the impedance that we see looking into nodes A and B is impedance A, then is in parallel with ZC plus ZB. And then the impedance looking in to AC, this impedance ZC is in parallel with the series combination of A and B. And then the impedance looking in nodes B, C is ZB, is then in parallel with nodes A and or with impedance A and C. So we have these three numbers or impedances looking into the network that we can measure, and from these we need to extract the values for ZA, ZB, and ZC. So try to think of a way you can solve this. If you use brute force, nodes, or mesh analysis, it's going to be an algebraic nightmare. There is a clever way to solve this with minimum algebra, but if you don't recognize a way to approach this problem, then the algebra is just going to be burdensome. It's going to be a formidable problem for you. It probably could be solved that way, but it's going to take you pages and pages. So this is the network. Is again, what we're trying to do is measure and determine ZA, ZB, and ZC indirectly by measuring the impedances looking back into the network between pairs of nodes. So what we want to do, what eventually want, is be able to express ZA as a function of ZAB, ZBC, and ZAC, and so on for ZB and ZC. So we'll call that f of A. ZB then will be f of B of ZAB, ZBC, and ZAC. And ZC will be some function of ZAB, ZBC, and ZAC. So we want to be able to determine these functions A, B, and C as that have these three variables in it. So we can think of this as 3 degrees of freedom, 3 space, and we want to determine ZA, ZB, ZC in terms of these values. So that is the problem. Now I'll show you how I solved it. Okay, the way I solved this network is I borrowed a transformation that's commonly used in the power industry in 3-phase power. It's called the Y to delta transformation and the delta to Y. We typically denote it as this way. We have delta to Y. This is delta, D-E-L-T-A, and this is Y spelled W-Y-E. And why I can use this transformation is this network is like a delta network. If we look, if I have here node A, node B, and node C, between A and B, there's ZA. Between A and C, I have ZC. And between B and C, it's ZB. So it looks exactly like a delta network. And this is completely equivalent to a Y connection if we appropriately choose the element values. If I call that Z2, and this is Z3, and this is Z1, this is a neutral node, it's called neutral node, that you don't have access to. But these two networks are exactly equivalent if you appropriately choose the element values. That is, if I look into nodes A and B, between that pair of nodes, I will see exactly the same impedance looking into nodes A and B, this pair of nodes this way, with appropriate choice of the element values. Now, the way that we choose the values is we define ZT as being the sum of all the elements in the Y network, or in the delta network. ZA plus ZB plus ZC. And I define P as being a sum of products taken two at a time in the Y network. So P is Z1, Z2 plus Z1, Z3 plus Z2, Z3. So with those definitions, we can write two equations. Equation 1, let's put that over here. So with equation 1, I can write that Z1 is ZB, ZC over ZT. Z2 is ZA, ZC over ZT. And Z3 is ZA, ZB over ZT. This is the transformation to go from delta to Y. We take our element values A, B, and C, and we compute what Z1, Z2, Z3 need to be to make the networks equivalent. And likewise, equation 2 is going to give me the conversion to go the other way. I'll define ZA, or ZA is P over Z1, ZB is P over Z2, and ZC is P over Z3. So this gives us the conversion going the other way. We can get the element values for the delta network given the Y network elements, and this gives us the transformation going from Y to delta. Now, with these, I'm going to use the Y connection here to write some equations. We're going to concentrate on the Y network. So Z AB is what? Well, node C is open circuited, so Z1 does not enter in. So the impedance looking in to the nodes A and B is just Z2 plus Z3. And Z AC, if we look in AC, it's just Z2 plus Z1. This is open circuited. Z3 doesn't enter in. So this is Z1 plus Z2, and ZBC is just Z1 plus Z3. Now, what I'm going to do is subtract off, rewrite these equations. I'm going to start subtracting. I'm going to subtract ZAC, or I'm going to take ZAC and subtract ZBC from it. So I can write ZAC minus ZBC. Well, what's AC minus BC? It's Z1 plus Z2 minus Z1, Z3. The Z1's cancel, so we end up with Z2 plus or minus Z3. And likewise, I can take, let's just do it that way, I can take ZBC and subtract ZAB, and I can take ZAB and subtract ZAC. Okay, ZBC minus ZAB is this minus that. The Z3's cancel, so we end up with Z1 minus Z2. ZAB minus ZAC is this minus this. The Z2's cancel. I end up with Z3 minus Z1. Okay, now what we want to do is form the sums. I'm going to add ZAC and ZBC minus ZAB. And then I will take ZAB and I will add ZAC minus ZBC. And then finally I'll take ZBC and add to it ZAB minus ZAC. Now, let's see what we get here. So to ZAC, I'm going to add BC minus AB. That is this equation here. I'm going to add to AC this amount right here. So what's ZAC? ZAC is Z1 plus Z2. That's ZAC, and I'm going to add to it this equation, which is Z1 minus Z2. And we see that our Z2's cancel, and we're left with 2Z1. Likewise, I'm going to take ZAB, which is Z2 plus Z3, and to it I'm going to add AC minus BC. AC minus BC is Z2 minus Z3. So our Z3's cancel, and we end up with 2Z2. And here I have ZBC, which is Z1 plus Z3. And to it, I'm going to add AB minus AC. AB minus AC is Z3 minus Z1. So our Z1's cancel. And we end up with 2Z3. Okay. Now, we solve for Z1, Z2, and Z3. Let's see here. Let's see, how do I want to do this? I'll just get rid of this here. So we can write the answer down now. Taking this equation and solving for Z1. So Z1 is equal to ZAC plus ZBC minus ZAB. And that's over 2. We can see this. It's ZAC plus ZBC minus ZAB. Likewise, Z2 is ZAB plus ZAC minus ZBC all over 2. That comes from this equation. AB plus AC minus BC. And then Z3 is ZBC plus ZAB minus ZAC all over 2. So that's our solution. if I measure the node pairs, these impedances, and I define my Z1, Z2, Z3 by these combinations of node pairs. Once I have my Z1, Z2, and Z3, I can compute what these individual impedance values are from this equation 2. We compute Z1, Z2, Z3 from Z1, Z2, Z3. We can compute P. Once we have the Z1, Z2, Z3, we can compute our P using these values. And once we have P, we can compute ZA, ZB, and ZC3 by those relationships there. Now, so that's how I solved it. Now, to test the theory, to make sure that it's correct, is I have some values. What I'm going to do is rewrite some of this. Just get all the way so I can take a look here at the work. Now I'm going to get rid of this. Okay, I'm going to rewrite my once I have Z1, Z2, Z3, I can compute my P, and then ZA, what I had over there is just P over Z1, ZB is P over Z2, and ZC is P over Z3. Okay, so that's how we do it. We measure our node pairs of impedances, compute our Z1, Z2, Z3 with these equations. Once we have our Z1, Z2, Z3, we can compute our P, and then we can compute ZA, ZB, ZC using this relationship. Okay, I had a network, or let's take a look at some values here. Suppose ZBC is 199. Let's just assume these are resistors. So if I start with my delta network, the impedance seen looking in here between these nodes B and C is 199. The impedance between nodes A and C is 206. And the impedance seen looking in between A and B is 47. Now we want to compute what ZA, ZB, and ZC are. Well, if you put in the values here, you can compute Z1, ZAC, this is ZAC here. This impedance is ZBC, and this impedance is ZAB. So we put in the values. ZAC is 206, BC is 199, we subtract off 47, divide by 2, and we get Z1. Z1 in this case comes out to 179, Z2 comes out to 27, and Z3 comes out to 20. Now, the p-value, when we put in Z1, Z2, Z3, p comes out to 8,953. And from that, we can get now our ZA, ZB, and ZC. This is Z2. So these values then, ZA is P, which is 1853, divided by Z1, 179. So this is 8953 divided by 179. And that comes out to 50.01676. ZC is 8953 divided by Z3, which is 20. And this comes out to 47.6000, and ZB then comes out to 331.59259. So these are the individual resistor values for ZA, ZB, and ZC. Now, to check this, all you need to do to check the theory here is, say, compute. I'll just do one of these. Suppose we want ZAB, the node pair ZAB. Remember, ZAB is looking in this network, which is ZA in parallel with the series combination of ZC and ZB. So this is ZA in parallel with the series combination of ZB plus ZC. Well, we can write for a parallel network, we take the reciprocals and work with admittances or conductances. So 1 over ZAB is 1 over ZA plus 1 over ZB plus ZC. If we put our numbers in for A, B, and C into this equation here, this comes out to 1 over 0.02128. So ZAB is the reciprocal of that. ZAB then is 47.0000, which is the value that we originally started with, the impedance looking in between nodes A and B. So that's how you can check, and they all check out. Now, I'll show you what the original network looks like, the resistor network. This is an example of the type of network that I'm talking about. I have 3 resistors that are tied together in this closed circuit in this loop, and I have access to 3 nodes. I have node A, B, and C. So this resistor here between A and C would be resistor ZC. Between A and B we have resistor ZA, and between B and C we have resistor ZB. Now, because they're soldered so close together, I wasn't able to break these resistors apart. If I was to take a diagonal cutter and free the one node so that I could measure the resistors directly, I'd never be able to get the network back together. There's a reason for having the resistors in such close proximity as this, is because it's to keep the lead resistances down and also keep them in thermal proximity of one another. This was in a precision amplifier network. So all I had access to were these three nodes in which I measure the resistance, say between nodes A and C looking in this way, then looking in this way between nodes B and C, and then looking in this way between nodes A and B. These are 1% resistors, and I'll be discussing this a little later on in the video, but I wanted you to see what an actual network of resistors looks like that we're talking about. Now that you've seen the original resistor network, looks something like this. I'll just kind of sketch it out here. Now that you've seen the original network, I'll sketch it out here. We have three resistors. They're tied together in a delta ring network. We'll call this node B. This is node A, this is node C, this is ZA, this is ZC, and this is ZB. Now, why I couldn't measure the resistors individually is you could see the network was, the resistors were soldered very close together. So if I was to try to break one of the nodes, I wouldn't be able to put the network back together because there wouldn't be enough pigtail lead left on the resistors. I had to put them very close together so that they'd be in thermal proximity to keep them stable temperature-wise, and also to reduce lead length errors. So my only option was to measure the impedance between the various nodes and then compute what the individual resistor values were to see if they had shifted. Now, the original resistors were 1% metal film resistors. 1% metal film. And I measured them before I put the network together and recorded the values, and these are the values that I started with. ZA was 74.945 ohms, ZB is 99.870 ohms, and ZC is 24.841 ohms. Now, I went ahead and measured these values, the node pair values, ZAB, ZAC, and ZBC. And the way this was done is I measured it 3 different times here recently using a HP 34401 digital multimeter. This is a 6.5 digit multimeter. Has on the order of a couple parts per million accuracy. Very good digital multimeter. So to measure the impedance or the resistance between node A and B, I first connected the meter, some leads here between A and B with the meter, and measured ZAB, that resistance. ZAB measured 3 different times, and I averaged the readings, and for ZAB is 46.804. Then went ahead and moved the multimeter over to another node pair for ZAC. For ZAC, we connect the probes between nodes A and C and measured ZAC between the 2 nodes with the multimeter. 3 readings, and I averaged them. Get 21.726 ohms. Then move the meter to the last node pair between B and C. So connect the leads here and measure ZBC. And ZBC, after averaging 3 readings, gave me 49.887 ohms. So those are the 3 readings. Now, with those readings, we go ahead and calculate the individual resistor values. We have ZAB, AC, and BC. We put in these equations here to get the Z1, Z2, Z3. Putting these values in, Z1 computes to 12.4048 ohms. Z2 computes to 9.3215, and Z3 computes to 37.4825. Now, using these values for Z1, Z2, Z3, we can calculate the P value. P came out to 929.989. Then, now with P and Z1, Z2, Z3, we can compute the values of the individual resistors, ZA, B, Z. Putting the values in for Z1, Z2, Z3 into these equations, ZA computed to 74.970, ZB is 99.768, and ZC is 24.811. Compare to the original values, and we see that we're very close. If we compute the errors, ZA is high by 0.031%. ZB is low by 0.10%, and Z3 is low by 0.12%. So I'm well within the margin of error. Remember, I start with 1% metal film resistors, and I compute that they're within 0.1% of the original values, so that they haven't shifted. So that wasn't the problem. That particular network was not the issue in this particular instance. So we see that the theory does check out. It works really quite well. I'd be interested in getting your comments on how you solved the network, if you did, if you found an approach similar to mine or found another approach. Please let me know in the comment section. So that wraps it up, and